Okay, this is going to be about the rotation of the galaxies and the big problem that general relativity doesn't seem to work, and so they've had to postulate dark matter to account for the high velocity rotations of these galaxies. So I've chosen two galaxies, Messier 31, which is known as Andromeda, and that's the top one here, Andromeda. It's about 2.5 million light years away, but it can be seen from Earth in the northern hemisphere, and it's about 200,000 light years across. And then it has a little satellite galaxy, which is this one down here, and that one's just beside it. Okay, and that's Messier 33, this bottom one, the black graph. Okay, so these graphs are in all sorts of units. They have funny units to try and reduce the size of the numbers. So looking at the top one, you're looking at kiloparsecs, and you're looking at kilometers per second, and the mass, they've done a funny unit, 10 to the power of 10 times solar mass units. So they've managed to get these numbers down to sort of 20 of those, and instead of just kilograms. And luckily the Messier 33 is also in kilometers per second, but the distance is in light years instead of kiloparsecs. But it's also got the difference between what general relativity says should be the rotation speed expected from visible disk, in other words, and then the actual rotation speed, which is this top one, and therefore you have to postulate dark matter to account for that fast velocity. Okay, and so general relativity says that there must be dark matter, but there's another one which is called modified gravity, and that one adds an acceleration factor. It's a low acceleration, but it's sort of inherent to the universe itself. It's just there, and it starts to affect the velocity of the stars as they get further and further away. Sort of like dark energy, might even be dark energy. It's very close in value to and I've actually calculated exactly what that universal acceleration would be with my little b on the left hand side here. I've got little b and the radius of the universe. So I've sort of constructed a universe, you could say. Why did I choose that for the b value? Because the age of the universe would then be 13.7 billion years, which is right. But the main reason I chose it is because of Robert Dickey's equation, where he says that the gravitational constant is related to the total mass of the universe. So he's come up with this equation, and it turns out that R and C cancel out completely, leaving me with just L cubed over T squared, which is mass times 4, and it comes to exactly 1 if I choose that B value, which means that gravity is what it is now. Okay, so there are other reasons why I've chosen that for the universe, because the vacuum energy is about right, 1.5 times 10 to the minus 9 joules per cubic meter, and also I get the right expansion rate, which is in kilometers per second per megaparsec, which is about 70.71. It gives me the right mass density. And anyway, here's the that would be the mass of the universe there in kilograms, 3 times 10 to the 53 kilograms. And anyway, here's the acceleration, universal acceleration calculation. First of all, I've just made it acceleration, meters per second squared. You have to divide by 4, so that's a new constant that I'm going to have to explain, the 4. But they don't know why it's close to the cosmological constant, which is 1 over m squared. So there I've just reorganized it, but it's still the same calculation. And here I've reorganized it again. You can see that L squared over T to the power of 4, that's actually pressure, or pascals, to pascals to be exact. So that's another way of looking at it, or there's another way of looking at it, where I put all the constants together on the right hand side. Okay, so that's the value I'm going to use to adjust the acceleration, which will up the velocity. Okay, so let's start with some calculations. So Andromeda, you can see if I'm always going to use mond, because that gives the right answers. So let's see, for a b value of 0.00077, I would put in a radius of 30,000 light years, and then I have to convert that to kiloparsecs, as I said over here, kiloparsecs. And you can see that mond says the velocity is going to be 270, which is about right, and it says it'll be that velocity, whereas general relativity says the velocity will only be 230 kilometers per second. And the acceleration there, and the distance, I'm looking at 9.9 kiloparsecs. So that works out, which is about 30,000 light years. And the mass, notice it only has to be 11. See, this is in those units. So it's basically agreeing with GR at this point, but then it doesn't drop down, as it just carries on. So we have to see why that is. So let's go to another b value. What am I looking for? Messier. Yeah. That. And let's jump that up to 70,000 light years away. Now I'm looking at a velocity of about 233, which is about the correct velocity for anywhere along there. Notice that GR is just totally crapping out now. It's saying the velocity should be down here. At what distance? 21. At a distance of 21. That's the distance. So mond is giving the right velocity. GR is saying the velocity should be somewhere down here. And what about the mass required? Well, according to mond, only requires about the same amount of mass, so don't need dark matter. Okay, now let's go to Messier 33, which is a little satellite one. This is the black graph. Let's start in close. And now I'm just got to put put light years now. Now I'm just going to put meters directly. 1.3 times 10 to the 20 meters. R is meters, as you can see up here. And Mond says the velocity should be 100. Ooh, need a different colour there. Better use white. So here's 100. That's 100 kilometers per second. So as GR is saying, the velocity will only be about 62 kilometers per second. And what was our distance in light years? 13 points, about 14. Yep, that's about right. It's about 14,000 light years, about there. So you can see Mond's giving the right answer. Let's go further out to say 55,000 light years, which is right out here now. So Mond should be about 120, whereas GR would say something else, about 50 or something, 40, 45 or something. So let's have a look at that. What do I need to put? Okay. So to get out there, the velocity should be about that, at a distance of about that. What does Mond say? 115 kilometers per second. That's about right. 115. GR is saying it will only be about 44 kilometers per second. That's this predicted by GR. That one. This one's predicted by Mond anyway, and that is what the data says. And 50,000 light years we're looking at. So again, Mond is still correct. Okay. And just to explain the Mond calculation, looks pretty complicated, but it's all I've done is add the universal acceleration to the acceleration that Newton would have said. So the clever little trick here is you just make m to the power of 4 and s to the power of 4 and then square root it twice, and by doing that you haven't changed your value. And now you can break up your m to the power of 4 over s to the power of 4 so that you can say mass times acceleration, and now you're free to add acceleration to that other acceleration, which is what I've done here, where I've added the universal acceleration, which is little m divided by little s squared, and then this 4, and that's how you now how does it work though? Let's go back to it's not allowed to crap out at say the Earth, on the Earth. So let's go to the Earth, which is a very small distance. So the surface of the Earth, what happens? Okay, what does Mond say? Oops. Yeah, that's right, because should get rid of that 1,000 really, because now we're just talking about meters per second, and that looks familiar, doesn't it? About 8,000 meters per second, 8 kilometers per second is the orbital velocity at the surface if there's no air, And here we have 9.8 is the acceleration, meters per second squared. Mond basically agrees with GR. You can see there's slight difference way down in the decimal points. You wouldn't even notice it, but that would actually prove Mond actually, if you could do it, if you could actually measure that with that accuracy, but you can't. And of course here's our mass of the Earth, so it works. I think that's all I need to say. Yep. Okay.